If you're interested, then this is for you if you're interested. I'm not gonna ask this, but you could go. So earlier we said that we saw that the number of possible subsets follows 2 to the power of the cardinality, but it's not sufficient to show with examples that the cardinality is 2 to the n. So consider this set here. So assume that the cardinality of k is equals to n. So how do we get subsets? We just remove one element at a time, right? So if we remove one element from k, then how many arrangements can we get from there if we remove one element from k? Or in fact, let us just use the idea of like, instead of grouping, let me just say it like this. If we choose only one element from k, then how many arrangements can we get? We basically get there are n combination 1 elements, the n combination 1 subsets possible. If we choose 2, then we get n combination 2 subsets, and repeat this until n, whereby there will be n combination n subsets. Also note that if you don't remove any element, then you have n combination 0 subsets. So it follows that you can basically just say that the cardinality of the power set of k is basically going to give us the sum starting from n combination 0 plus n combination 1 plus n combination 2, and you can only repeat this process up until n times because you have n elements. So basically it follows that you just have a sum, say maybe where k goes from 0 to n of n combination k. So this is the cardinality of a power set of a set consisting of n elements. But earlier we claimed that it's 2 to the n. So let us claim that now. But when we do our proof, we see that it's this one. So now claim that 2 to the n is equals to the sum from where k goes from 0 to n of n combination k. So now you want to basically prove your claim. So it is sufficient to just show this one. Of course, then we can use induction. Base case, you choose n to be 0. So the left hand side basically gives you 2 to the 0, which is 1, and the right hand side is basically giving you 0 combination 0, which is 1, which is the same as the left hand side. So the base case is true. Then now you recall how we used to do it, né? So you just assume, right? So assume that you have 2 to the m. I can't use k because I already used k there. Is equals to this for some m equal or greater than 0. Now we want to prove that 2 to the m plus 1 will then be something like this. Right? So if you can show that, then we basically proved that the cardinality is then 2 to the n for a power set of a set consisting of a cardinality of n. So how do we show this actually? How do we prove using induction that we basically have something like that? So notice that we basically, this is our assumption, and we want to somehow show this actually. So observe that you have something like this, m plus 1 to the power, m plus 1 combination k, which just basically, if I think like later if you guys are doing 1644, then you see that you'll deal with combinations, but a combination just basically tells you that you have m plus 1 factorial over m plus 1 minus k factorial by k factorial. So that's basically what we have. Of course, then we can then say that this is the same as when we go from this, then m plus 1 factorial. You remember what factorial means. So this is m plus 1 multiplied by m factorial. And then you basically have m plus 1 minus k multiplied by m minus k factorial multiplied by k factorial. So this is basically what we have. What we want is we want to obtain m combination k, or in other words, what we want is we want to obtain m factorial over m minus k factorial, so multiplied by k factorial. Then we can then use the assumption and use the 2 to the m from there. But so far you see, okay, I have the m factorial, I have the m minus k factorial, I have the k factorial. So you can then group that together, right? So you have k equals 0, you have m plus 1 there. So you have m factorial, then you have m minus k factorial, and then you have k factorial from there. But then that is multiplied with m plus 1, and then you divide that by m plus 1 minus k from there. Of course, You can do a little manipulation technique. Just copy the denominator as it is, meaning that you can then subtract a k and then add a k. If you just copy the denominator as it is, because then basically what we want is we want to have a 1 from there. So then we have that the sum from 0 to m plus 1 of m factorial over m minus k factorial by k factorial into 1 because of this one, right? If you divide m plus 1 minus k by this one, you have 1, then plus k over that. So we have plus k over m plus 1, then minus k. Then you have something like that. And then you have k equals 0 to m plus 1 of m factorial over m minus k factorial by k factorial, then plus m factorial k divided by m minus k. But what happens when you multiply this one with this one here? You get m minus k plus 1 factorial, right? Then by k factorial. But then now you obtain, you can then split the sums. M minus k factorial by k factorial plus the sum of this one. But what is k over k factorial? Notice that k over k factorial is basically the same as k by k times k minus 1 factorial. So you are left with 1 over k minus 1 factorial. So you can just transform that one to that. So you have m plus 1, k is 0, and then you basically have m factorial divided by m minus k plus 1 factorial multiplied by k minus 1 factorial, which you can then, this one you see that is then immediately the combination, right? So you can then say that you have m combination k plus the sum from 0 to m plus 1. But do you see that here you can rewrite m minus k plus 1 as m minus k minus 1, and then it immediately follows that you have m combination k minus 1 from there. So you have something like this. So this is what we have. So using what we have to m combination k plus, now you put m plus 1, right? You evaluate that thing at m plus 1. So you have m combination that. Now this one here, you're gonna treat it like you can do some adjustment to it such that you can replace then, I mean, if you use some other variable from there, maybe t, and you replace t with minus 1, maybe. Sorry, if you replace t with k minus 1, if k is 0, then t is minus 1. And so basically you have something like that. But if then k is m plus 1, if you plug m plus 1, then you just have m there. And so then you basically have m combination t. Of course, you cannot arrange, how many times can you arrange two things into groups of three? You can't, right? You can't arrange, you can't make arrangements on, like, you are short of one, basically. That's what's happening here. So that's why this immediately goes to 0. And this one here, you can then break it down to So we are left with something like this: k equals 0, m combination k plus this one. So you can remove the term with the minus 1 there. So then you have m combination minus 1. You can't really arrange negative times, so it goes to 0. So then you have something like this. T goes to, I mean, now it's 0. So then you have m, then you have m combination t. And so you basically left with this one: k equals 0, m. Do you see that these two things are then similar? So you can rewrite it as 2 times this one, m combination k. And then you have 2 times 2 to the m. This here is by assumption. Sorry, by assumption. So, sorry, it should be by assumption, and it immediately follows that you have 2 to the m plus 1 as desired. That's what you wanted to show. You just showed this. So yeah, then you're done. That's how you show that the power set has the cardinality of yeah, you're not gonna get asked this, so it was just for if you're interested, then that's how it goes. Like, it's a really nice proof, to be honest. So that's it. Then see you guys tomorrow.